Welcome back. In this video, we start with Chapter 5 about LP spaces. There will be two sections in this chapter. The first one that we'll cover in this video is mainly a review of last year, because in principle you studied LP spaces in the second course on measure theory and integration. Okay, so what are the LP spaces? First, let us consider the case where P is a finite number, which is at least 1. And suppose that we have a measure space, X A mu, which means that X is a set, calligraphic A is a sigma algebra of subsets of X, and mu is a measure on XA. We denote by calligraphic LP of X the set of all real valued functions from X on X, whose pth power is summable or integrable, if you like. Okay. So, of course, we need to, when we talk about summability, we need to include the assumption of measurability, because if f is not measurable, you cannot talk about the integral of f or f to the p. Okay, so, but there are other notations as well. The full notation is LP of X A mu, okay? And we can sometimes write LP of mu. This notation is useful when we have two measures on the same space, mu1 and mu2, and we want to compare them, then we write LP of mu1, LP of mu2. And if it's clear from the context, we just write LP. Now, it should be clear that LP is a vector space because it's a subspace of the space of all real valued functions on X, equipped with the usual addition and multiplication by scalars. So why this is true? Because if f and g are in LP and alpha and beta are constants, then the linear combination alpha f plus beta g is of course measurable, as you know from measure theory. And it's easy to prove this identity. Alpha f plus beta g to the power p is less than 2 to the p times alpha p f p plus. Okay, actually we can prove a better estimate. And we can write instead of 2p 2 to the p minus 1, and this is just a convexity inequality. But it's not important here, because if this is true, when we integrate, since integration conserves inequalities, then we have that the integral of alpha f plus beta g to the p is finite. Okay, it's less than these two integrals. Okay, so this means that LP is stable under addition and multiplication by scalars. So it's a subspace of the vector space of all functions from X to R. Now, if f is an LP, we set norm p of f to be the integral of f to the p raised to the power 1 over p. Okay, this is now a finite number. And strictly, we called it norm, but actually it's not, strictly speaking, a norm. It's just what we call a semi-norm, because first of all, it's non-negative, because the integral is non-negative. It's homogeneous because you can put the constant outside, and it satisfies the triangle inequality, which is known in this case as the Minkowski inequality. And in principle, you proved this in a previous course. I'm not going to reprove it here, but it's not something trivial actually. And however, so if f is 0, then the norm p of f is 0, but the converse is not totally true, in the sense that if the norm of f is 0, we can only, so the integral is 0, we cannot deduce that f is the 0 function. We can only conclude that f vanishes almost everywhere. And this is something usual in measure theory. Most of the inequalities and equalities hold almost everywhere, so except on a set of measure 0. Okay. But now we'll see in a moment how we can turn this semi-norm into a norm. Okay. But before we do that, let us see what happens in the case p equal plus infinity. So what is L infinity of x? It's simply the set of measurable functions from X to R, which are what we call essentially bounded. So it means that the absolute value of f of x is less than a certain constant almost everywhere on X, so except on a set of measure 0. Okay. So we can say that L infinity is the set of measurable functions that are essentially bounded, and the constant C is called an essential bound of F. Okay, so of course we have other notations, L infinity of xa mu, L infinity of mu, or simply L infinity. Okay, so now we have a family of, this is of course a subspace of the space of all functions from x to r. So, and this is not difficult to see, because if f and g are in L infinity, alpha f plus beta g is measurable, and it's essentially bounded by absolute alpha c1 plus absolute beta c2. So this is a subspace of the space of functions from x to r. Now, the norm infinity of f is, in some sense, the smallest essential bound. Okay, so it's the infimum of the set of all constants that bounds from above f almost everywhere. Okay. And you can prove actually that this is a semi-norm, and the norm infinity is actually an essential bound. So absolute value of f of x is less or equal than f infinity almost everywhere. So the infimum is a minimum actually. Now, what is the relation between this L infinity norm and the supremum norm that you learned in second year or first year, the norm of uniform convergence? When f is continuous and bounded, it's the same actually. So if f is continuous and bounded from Rn to R, then the supremum of absolute value of f of x when x is in Rn is simply this L infinity norm. Why? Double inequality. So first of all, we know that f of x is less or equal than the norm infinity of f almost everywhere. But actually this inequality holds everywhere. Why? Because the set of x where f of x is strictly bigger than the norm infinity is open, because f is continuous. And it's negligible because norm of f is less or equal than f infinity almost everywhere. Now, an open negligible set must be necessarily empty, because if it's not empty, then it contains a ball, and the ball has positive Lebesgue measure. Okay, so here we are talking about the Lebesgue measure on R. So therefore, the supremum norm is less than the infinity norm, and conversely, since f is less than the supremum of f, then sub f is an essential bound, but norm infinity is the smallest essential bound. Therefore, the norm infinity is less than the supremum, and therefore we have equality. So the two notions coincide. Okay, so they have the same. So of course, the L infinity norm is more general than the maximum norm that you learned in previous courses. Okay, now we'll turn these semi-norms into norms. Okay, so for this, we introduce on the calligraphic LP spaces an equivalence relation. So it means that we identify functions that are equal to each other almost everywhere. So this is of course an equivalence relation because f is related to itself, it's symmetric, and it's transitive. So it's an order relation. It's an equivalence relation, excuse me. And therefore, we can talk about the quotient set of this relation. It's the set of all equivalence classes. So we put on the same class all the functions that coincide with each other almost everywhere. Okay. And the quotient set for this relation is denoted by capital LP of x. So here we have a slight distinction between calligraphic LP and capital LP. Okay. And so an element of capital LP is by definition a class of functions. So an element is a class of functions that coincide almost everywhere between each other. And now we can put a structure of vector space on this capital LP, as you've probably done in algebra. So given two classes, so we denote the class containing f by f between brackets. So what is the sum of two classes? The sum of two classes is simply the class containing the sum, and you can prove that this is independent on the representation. So if you take f prime in the same class of f and g prime in the same class of g, then f plus g is equivalent to f prime plus g prime. So, and similarly, a multiple of a class is the class containing the multiple. So this puts a vector space structure on capital LP. Okay. And the zero element is the class containing zero. Okay, so it's the set of all functions that are zero almost everywhere. Okay, and now we put a norm on this capital LP space. The norm of a class is simply the norm of any element in this class. Because if f and g or f and f prime are equal to themselves, to each other almost everywhere, then they have the same p norm. Okay, so therefore this makes sense. And now we can easily check that this is a norm on capital LP. Okay, now in practice, we write norm P of f or norm LP of f instead of the norm of the class containing f. And you think of elements of capital LP as functions that are only defined almost everywhere and not as classes. Okay, so we can write let f belong to LP. Okay. So it makes no sense in this interpretation to talk about the value of a function on a set of measure 0. So an important remark, if we equip 0, 1 with the Lebesgue measure, this is implicit in the definition. So when we write nothing, the interval 0, 1, open or closed, are actually is equipped with the Lebesgue measure. So now in this case, LP of the closed interval 0, 1 is the same as LP of the open interval 0, 1. Why? Because the Lebesgue measure of a point is 0. Okay, so actually these spaces are isomorphic. Okay, so we can identify them. Because it doesn't really make a big difference if f is not defined at 0 or at 1, because 0 and 1 have Lebesgue measure 0. And this common space is simply denoted by LP of 0, 1 between brackets. Okay, so then when we write nothing, once again, it means that 0, 1 is equipped with the Lebesgue measure. Second important remark, as you probably know from measure theory, if mu is the counting measure on the set of non-negative integers. Okay, so what does it mean? It means that mu of a subset of n is simply the number of elements in the set, and plus infinity if the set is finite, and plus infinity if the set is infinite. So this is what we call the counting measure. And now you probably proved that if g is a function from the integers into R, a function from the integers into R is simply a sequence. Okay, if g is such, so it's automatically measurable actually, because the sigma algebra on n is P of n, so any function is measurable. There's no. Okay, so if g is either non-negative or mu summable, then the integral of g with respect to the counting measure is simply the series of a general term g of n. Okay, so this is one of the advantages of the Lebesgue theory over the Riemann theory, that it includes series and finite sums as a special case of integrals. Okay, so therefore, what is capital LP of n P of n mu? It's simply the space small LP, the space of sequences xn, such that the series of a general term xn to the p is finite, is convergent. Okay, because when we raise this to the power p, you just get x of n to the power p. So small LP, the small LP spaces, including p equal infinity that we encountered in chapter 0, are particular cases of the Lebesgue spaces capital LP. Okay. Okay, this is because of, so everything follows from the definition. When p equal infinity, the f infinity norm is the max, the supremum of x to the n or f to the n. So this is. So everything we prove for general capital LP spaces applies to small LP spaces of sequences. Now I will just mention, without proof, some of the main results that we proved in Math 3306, the second course on measure theory and integration. First of all, capital LP equipped with this norm is a Banach space, so it's complete. Okay, this includes the whole range of P from 1 to infinity inclusive. So in particular, when P equal 2, we get a Hilbert space. Now, what happens if P is less than 1? Well, if P is less than 1, we can always talk about the LP spaces, but then this is not a norm anymore because the Minkowski's inequality is not satisfied if P is less than 1. Okay, next result in the proof of the completeness of the LP spaces is that if you have a sequence Fn of LP that converges in LP, in the norm of LP to some function f, then we can deduce that there is a subsequence Fnk that converges almost everywhere, so pointwise almost everywhere, to f. And this sequence is bounded from above by an element, by a function in LP. Okay. Second result, if Xa mu is a finite measure space, then the sequence LP is decreasing. So we have L infinity is contained in LQ, is contained in LP, is contained in L1. But this does not hold if mu of x is equal to plus infinity. And however, if you consider the small LP spaces of sequences, this sequence or this collection LP will be actually will be increasing instead of decreasing. So pay attention to this difference. If you, for example, take x equals 0, 1, then L infinity of 0, 1 is contained in LP of 0, 1, contained in L1 of 0, 1. But if you consider the space of sequences, we have small L1 contained in small LP contained in small L infinity. Okay. And so this is a remark that this result does not hold if the measure of the space is infinite. Okay, so for example, if you consider the function from R to R given by 1 over radical x squared plus 1, then this function belongs to L2 because its square is just 1 over x squared plus 1, and its integral from minus infinity to infinity is convergent. So, but this function is not in L1 because its integral is infinite. Okay, now last thing is about the density of the continuous functions with compact support. So if omega is a subset of Rn, which is Lebesgue measurable, then we consider omega as a measure subspace of Rn equal to the Lebesgue measure, okay, that we denote by lambda capital N. Okay, so in this case, as a notation, we write LP of omega as the space of functions from omega into R, which are Lebesgue measurable and whose pth power is summable. Okay. So when we write nothing, it means that we equip omega with the Lebesgue measure. Okay. And this is a very important case in the theory of partial differential equations. And L infinity of omega denote the same thing. Okay, now what if for a continuous function, what is the support of a continuous function? The support of a continuous function is the smallest closed set on which f does not vanish. So in principle, encountered this notion before, and it's important. Now we have a very important space that we denote by CC infinity of omega. It's the space of all functions f from omega to R whose support is a compact subset of omega, which means that f vanishes outside a compact set. This space is very important. Why? Because one of the reasons is this density theorem that you probably encountered last year. If omega is an open subset of Rn and P is a finite number bigger or equal than 1, then this space, CC infinity of omega, is dense in LP, which means that any function, any element in LP can be approximated in the LP norm by functions which are very smooth. So because this is important, because elements in LP need not be even continuous, okay? Because the condition of belonging to LP is just an integrability condition. So it says nothing about the smoothness of the function. But what this theorem says is that any element in LP, any function in LP can be approximated by a sequence of very smooth function, very nice functions. And this result does not hold if p is equal to plus infinity. Okay, so and the last result is the following. L1 log is the space of Lebesgue measurable functions from omega to R that are summable on every compact subset K of omega. Okay. So it's a very important space, L1 log. So locally integrable or locally summable function on omega. Okay. Integrable, summable, same thing. Okay, so the last result is sometimes known as the fundamental lemma of the calculus of variations. If U is locally integrable on omega, omega is an open subset of Rn equal to the Lebesgue measure, of course, then, and the integral of U phi is 0 for every phi in CC infinity of omega. Okay? By the way, in this distribution theory, if you learn, this is called the space of test functions. Okay, so if the integral of U against any test function is 0, then necessarily U is 0, and of course, almost everywhere. If U is continuous, then we can deduce that U is 0 everywhere. Okay, so let us present a simple proof of this theorem in a particular case when U is just L2. Of course, L2 is contained in L1 log. L1 log is bigger than L2 and bigger than LP. Okay. You may study in more details these spaces next semester. So I want to prove that U is 0 almost everywhere. So it's enough to prove that the absolute value of U is less than epsilon almost everywhere for every epsilon. So if epsilon is given, the density theorem, the previous density theorem 5.2, tells me that I can approximate U by a very smooth function phi in CC infinity of omega in the L2 norm. So the norm 2 of U minus phi is less than epsilon. So now if I go back to the definition of the norm 2 of U to the square, it's just by definition the integral over omega of U squared with respect to the Lebesgue measure. Usually we skip it because it's clear from the context. Now I write U as U squared, of course, and since the integral of U phi is 0, then the integral of U squared is just the integral of U times U minus phi. And now if I apply the Cauchy-Schwarz inequality, I see that this integral is less than the norm 2 of U times the norm 2 of U minus phi. And this is less than epsilon times norm 2 of U. And now, if the norm 2 was not 0, then the norm 2 will be less than epsilon. But this is true for every epsilon, then we deduce that the norm 2 is 0. And this is a contradiction. Therefore, we must conclude that the norm 2 of U is 0. But if the norm 2 is 0, then U is 0 almost everywhere. And that's it. The proof of the general case can be found in chapter 4 of the book of Bresis. So this concludes this video and section 5.1, which was mainly a review of these important spaces in analysis and the theory of partial differential equations. So thank you for your attention and see you next time.